Okay, so we're looking at finding approximate areas underneath the curves and getting these approximates to look really accurate. And so I'm going to introduce the trapezoid rule. At this point in time, what we've learned is that if I take a curve like this and if I put on some rectangles, if I put up rectangles here, I can see that this overestimates it, and if I go to this side, that underestimates it. Even if I go to the midpoint, you can kind of average it out, but it's still going to be an estimate. One of the things that we can do, as opposed to doing rectangles, is we can add trapezoids. We can change them to trapezoids, and we can look at, it seems to fit the curve better, and if I increase the number of trapezoids, you can quickly see that it approximates the area quicker than rectangles do. And so that's the premise of the trapezoid rule. And so if I consider this, let me get this to 2. Okay, I can see that when I look for the trapezoid, here's my height, and then here's base 1, and here's base 2. Here's my height, base 1, and base 2, and then this base 1 is used twice. And so we're going to actually derive the trapezoid rule. So what happens with the trapezoid rule? I know that the area of a trapezoid, that is equal to half the height times base 1 plus base 2, whatever they may be. And we'll call b sub 1 plus b sub 2. Okay, and so the height, when I think about it, the height is going to be this distance here. The height is going to be delta x, because I always have to have a height and the base have to be perpendicular to each other. And the construction of the x-axis and these lines make this the height. It's a perfect height. And then what I'm going to do is I'm going to, well, if I'm going to look at this first triangle here, or the first trapezoid here, my base 1 is going to be y0 plus y1. And that is going to be the area of this particular trapezoid. But then what I'm going to do is I'm going to go find the area of the next trapezoid, which is going to be half the change in x, which is my height, times y1 plus y2. Plus, and this is going to go on forever and ever, and I'm going to have 1/2 plus delta x times, what I'm going to do, I'm going to have, well, yn minus 1 plus yn. And to find my delta x I know is just going to be the difference between this value of b and this value of a, the subtraction of those, divided by however many intervals I want to have, and that's going to be my change in x. So if I look at this formula here that I've created, I'm going to pull out a factor of 1/2, and I'm going to pull out a delta x, and when I do that, I end up with y0 plus y1 plus y1 plus y2 plus, inside here there'll be another y2 plus dot 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 plus, well, when I go backwards, there's going to be a yn minus 1 plus a yn minus 1, because it's going to be on this rectangle. This n minus 1 will be used twice, but yn is used once. So here's kind of the key, is yn, the last one and the first one, are only done once, but all the other ones, all these ones, are done 2 times. And so when I keep going on this, I get 1/2 delta x, and I can say it's y0 plus yn plus 2 times y1 plus y2 plus yn minus 1. And this here is in essence the area underneath the curve. This is the trapezoid, is approximately equal to this calculation here. And if we look in our formula booklets, this is what our formula booklets say. We have the area underneath the curve, that's what this is, the area function here, is equal to half the height, which is going to be my delta x, this calculation here, with the first, this is the first and the last value, plus 2 of all the other ones going through. So that is how the trapezoid rule is derived.